Welcome to the Curious Voyager. Tonight, let yourself sink a little deeper into wherever you're resting. There's nowhere to be, nothing to solve, no thought you need to finish before morning. Let your shoulders come down from wherever they've been holding. Let the weight of the day settle out of your hands. We're going to take a slow walk together toward one of the strangest, gentlest facts in all of physics, and there's no hurry to arrive. The path itself is the point. So breathe out, slow and long, and let me tell you about a wall that a particle should never be able to cross, and yet crosses, quietly, countless times a second, in the heart of the star that keeps us warm. Let's begin with that star. The sun. You know it as the thing that rises, the thing that gilds the tops of trees in the late afternoon, the thing that has poured light onto this planet for longer than there have been eyes to catch it. And at the center of the sun, in its deepest core, the temperature reaches about 15 million degrees. 15 million Kelvin. Say that number slowly and it sounds like the hottest thing imaginable, a furnace beyond any furnace, a heat that no material on Earth could survive for even an instant. And here is the first strange, soft paradox of the night. 15 million degrees is far too cold for the sun to shine. Let that settle for a moment. Too cold. Not too hot, too cold. By the ordinary rules, the rules that govern billiard balls and thrown stones and everything your hands have ever touched, the core of the sun does not have enough heat to do the one thing we know it does. It should not burn. It should sit there, dense and dark and silent, a great cooling ember. And yet above us, right now, on the other side of whatever roof or window is near you, that same sun is pouring out the light of 100 billion trillion candles, and it has been doing so for 4.5 billion years. How? How can something be too cold to burn? And burn anyway? The answer to that question is the whole of tonight's journey. And the answer is a thing so quiet, so unassuming, that it took some of the sharpest minds of the last century to even notice it was there. The answer is that the particles in the sun's core do something they are not supposed to be able to do. They pass through a wall, not over it, through it. Through a barrier they do not have the energy to climb. And the name we give to that impossible everyday passage is quantum tunneling. But I'm getting ahead of the story. Let's slow down and walk up to that wall together, gently, so we can really see it. To understand why the sun should be too cold, we have to understand what it is actually trying to do down there in its core and why it's so hard. At the very center of the sun, the fuel is hydrogen, the simplest, lightest stuff in the universe, mostly just single protons. Single, positively charged particles, packed together at enormous density. And the sun makes its light by fusing those protons together, joining them step by step into heavier things and releasing energy each time it does. Fusion, two become one, and light spills out of the joining. That sounds simple enough. Push two protons together until they stick. But here is the trouble, and it's the trouble at the heart of everything tonight. Protons are positively charged, and things that carry the same charge push each other away. You felt a version of this yourself if you've ever tried to press the wrong ends of two magnets together. That soft, invisible resistance, growing firmer the closer you push. A springiness in empty space that won't let the two surfaces meet. Two protons feel exactly that, but far, far more fiercely. The closer they come to each other, the harder they push apart. And near the very end, in the last tiny stretch of distance before they could actually touch and fuse, that pushing apart becomes tremendous. It rises like a hill, steeper and steeper, into a peak. Physicists have a name for that hill of repulsion. They call it the Coulomb barrier, after Charles Augustin de Coulomb, who first mapped out the law of how charged things push and pull. Picture it, if you like, as a real hill in a dark landscape, a smooth slope rising up in front of each proton, blocking the way to the summit where fusion waits on the far side. To fuse, a proton has to get to the top of that hill and over. And getting over means having enough speed, enough energy to climb the whole slope against that ever-strengthening push. Now heat, in a place like the sun's core, is really just motion. Temperature is the name we give to how fast the particles are jostling and racing about. 15 million degrees means those protons are moving astonishingly fast, careening through the dense plasma, colliding, rebounding. You'd think that would be more than enough. But when the physicists did the arithmetic, when they measured how high the Coulomb barrier stands and how much energy a proton carries at 15 million degrees, they found something deflating. The typical proton, even at that unimaginable temperature, is moving nowhere near fast enough to climb the hill. It races up the slope, slows, stalls partway, and slides back down, turned away. Again and again and again. Like a tired traveller trying to walk up a hill of ice, getting a little way up and always sliding back to the bottom. By these classical rules, the honest common-sense rules of energy and motion, almost no proton in the sun ever reaches the top of the barrier. The number that would have enough energy to climb over is so vanishingly small that if that were the whole story, the sun would barely fuse at all. It would not shine. It would be, for all practical purposes, cold and dead. And yet, there it is in the sky. So something is wrong with the common-sense picture. Something is happening that the hill and traveller image leaves out. And to find it, the physicists had to stop thinking of the proton as a tiny hard ball, a little marble with a definite position, and start thinking of it as something stranger and softer. Something more like a wave. This is the turn where the world stops being solid, so let's take it slowly, because it's the loveliest idea in the whole night. In the world we can see and touch, a thing is in one place. Your hand is here, not there. A stone thrown at a window is either on this side of the glass or that side. There is no in-between. But in the deep, small world, the world of protons and electrons, the world quantum mechanics describes, a particle isn't quite a point sitting at a single spot. It's smeared out. It's described by something the physicists call a wave function, and the easiest honest way to picture a wave function is as a kind of cloud or a swell of water spread across space. Where the wave is tall and strong, the particle is likely to be found. Where the wave thins away to almost nothing, the particle is unlikely to be there. The particle doesn't have one location. It has a spread of possibilities, a landscape of probably here, less likely there, almost never over there. Now bring that wave up to the wall. Bring it up to the Coulomb barrier, that hill of repulsion. If the proton were a hard little ball without enough energy, the story would end at the base of the hill, bounce back, turned away, full stop. But the proton is a wave. And when a wave meets a barrier, something remarkable happens. Most of the wave does turn back. Yes, most of it reflects, just as common sense expects. But the wave doesn't stop dead at the wall like a ball would. Instead, it seeps into the barrier. It leaks into the forbidden hill itself. Inside that wall, inside the region where, by all the old rules, the particle simply cannot be, the wave doesn't vanish all at once. It fades. It dies away, smoothly and steadily, dimming as it pushes deeper into the barrier. The physicists have a beautiful word for a wave that behaves this way. That decays instead of oscillating. They call it evanescent. Evanescent, the same root as vanishing, a thing in the act of fading away. Inside the wall, the proton's wave is evanescent, dimming with every step it takes into the forbidden zone. And here is the whole secret of the night, the entire quiet miracle, resting on one small word: dimming is not the same as gone. If the wall is thick, the wave fades to essentially nothing long before it reaches the far side, and the proton is turned back after all. But if the wall is thin enough, if the barrier is narrow, then the wave, though faint, though dimmed to a whisper of its former self, is still just barely alive when it reaches the other side. It emerges on the far slope of the hill, a ghost of a ripple, small but real, and because the wave is still there on the far side, however faintly, there is a real, honest, non-zero chance that the proton is there too. On the other side of a wall it never climbed. Having crossed a barrier, it never had the energy to cross. That is quantum tunneling, that's the whole of it, in its gentlest form. The particle doesn't smash through the wall. It doesn't borrow a burst of energy and leap over the top. Nothing bores a hole, nothing tunnels in the way a mole tunnels through earth, despite the name. The word tunneling is just a picture we reach for, and like all pictures, it's a little wrong. What really happens is softer and stranger than digging. The wave that describes the particle simply leaks through the forbidden region and comes out faintly alive on the other side. The proton was never really a hard ball that had to climb. It was always a spread-out swell of possibility, and possibility, it turns out, can seep through walls that a marble never could. Let me give you an image to hold on to, one to carry through the rest of tonight, because we'll return to it more than once. Think of a stone seawall standing against the ocean and the waves rolling in against it in the dark. Most of each wave, of course, breaks against the wall and rolls back, the great bulk of the water turned away, just as you'd expect. But if the wall is thin and you stand on the sheltered side and rest your hand very lightly against the inner stone, you might feel it. A faint tremor. A ghost of the wave on the far side, having passed through the barrier not as water pouring over the top, but as a disturbance carried through the very body of the wall. The particle is the wave. The tremor on the sheltered side is the escaped probability. Most reflects. A little leaks through, and in that little leak lies the light of the sun, because now we can go back to the star and understand what's truly happening in its core. Those protons, racing about at 15 million degrees, almost never have enough energy to climb the Coulomb barrier. That much was true. The common-sense picture wasn't wrong about that. But protons are waves, and waves can leak. So every so often, not by climbing, but by tunneling. A proton's wave seeps through the barrier and finds a second proton on the other side, and the two of them, at last, can fuse. Now, the sun's fusion doesn't happen in one clean step. It happens as a chain. A patient sequence the physicists call the proton-proton chain, the main way a star like ours turns hydrogen into light. And the very first step of that chain, the one that gets everything else started, is the hardest of all. It's two protons coming together to make a thing called deuterium, a heavier form of hydrogen, a proton and a neutron bound together. And to make deuterium, two difficult things have to happen at the very same instant, which is why this first step is such a tremendous bottleneck. The first difficult thing you already know: the two protons have to tunnel through the Coulomb barrier to get close enough to interact at all. That alone is rare. But there's a second difficulty layered on top of it. Two protons on their own can't simply stick together. Two positive charges bound side by side wouldn't hold. For them to form deuterium, one of those protons has to change, in the very moment of contact, into a neutron. It has to shed its charge and transform. And that transformation is governed by one of nature's shyest, slowest forces, a force the physicists call the weak interaction. The same gentle influence responsible for certain kinds of radioactive change. The weak interaction is, true to its name, weak, which here means it acts rarely, reluctantly, only now and then. So the first step of the sun's fusion asks for two rare things at once. Tunnel through the wall, rare, and in that same fleeting instant have a proton convert to a neutron by the reluctant weak force, rare again. Both together in the same breath. It's like asking for two unlikely coincidences to line up perfectly, over, and only counting the moments when they do. And this is where we arrive at one of the most soothing facts I know. Because these two things are each so rare and both required together, the whole first step is extraordinarily slow. How slow? Take a single proton in the sun's core, one particular proton, jostling in that dense hot plasma. How long, on average, must it wait before it finally fuses with another? Not seconds, not years. On the order of 1 billion years. 1 billion years of waiting, of near misses, of tunneling attempts that don't quite find a partner in the right state, before that one proton at last takes its first step into becoming light. Isn't that a strange and gentle thought to rest on? The sun is not a violent, frantic thing at its heart, burning through its fuel as fast as it can. It's the opposite. It's almost unimaginably patient. Each proton waits, on average, 1 billion years for its turn. The fire of the sun is a slow fire, the slowest fire there is, precisely because tunneling and the weak force make that first step so beautifully improbable. And that slowness is exactly why we're here. If fusion in the sun were easy, if protons could just climb the barrier freely, or fuse the moment they met, the sun would have burned through its hydrogen in a geological blink, a brief brilliant flare and then darkness, long before life could ever have gathered itself on a planet nearby. It's the rarity, the reluctance, the billion-year patience of each proton that stretches the sun's life across billions of years. Long enough for oceans to form. Long enough for the slow business of living things to begin. We are here, resting tonight under a stable star, because the crossing of that wall is so wonderfully hard. And the sun looks after itself too, through this same delicate mechanism. It holds itself steady with a kind of quiet self-regulation. Because tunneling is so exquisitely sensitive to energy, to temperature. The rate of fusion in the core is tied very tightly to how hot it is. If the core were to warm up a little, the protons would move faster, tunnel a touch more easily, and fusion would speed up. But more fusion means more energy pushing outward, and that extra push makes the core swell ever so slightly, and swelling makes it cool again, and cooling slows the fusion back down. And the reverse holds just as gently, cool a little, fuse a little less, contract, warm back up. Back and forth, forever, a slow breathing balance. The sun does not race, and it does not stall. It settles into a steady glow and holds there, self-correcting, century upon century, a great warm heartbeat regulated by the leaking of waves through a wall. There is something deeply restful in that, a star that keeps its own balance, asking nothing of us, simply holding steady overhead while we sleep. So there it is, the answer to the paradox we started with. The sun is too cold to shine, and it shines anyway because its protons don't climb the barrier, they tunnel through it. The light on your face on a summer morning, the warmth that has coaxed every green thing out of the ground since the beginning of the world, all of it comes seeping out of a wall that, by the old rules, should have turned every proton away. The most familiar thing in the sky runs on the strangest trick in physics, performed so quietly, so constantly, that we never feel the strangeness at all. We just call it daylight. Now, if this were the whole story, it would already be enough for one night. A particle that passes through walls, and by doing so lights a star, that's a fine thing to fall asleep on. But there's a deeper mystery folded inside this one, and it's the real reason we've come. Because so far I've told you that the particle crosses the barrier. I've told you it leaks through, that its wave seeps into the forbidden region and comes out faintly alive on the far side. But I've been quiet about one thing, and it's the thing that has troubled physicists for nearly 100 years, the question that is, even now, tonight, as you lie here, genuinely unsettled and openly argued about in laboratories around the world. Here is the question. When the particle is inside the wall, when it's there in the classically forbidden region, in the place it has no right to be, how long does it spend there? Think about how odd that question is. In the ordinary world, if you walk through a doorway, it takes you a certain time to cross the threshold. You could measure it with a stopwatch, a fraction of a second from one side to the other. But the barrier the particle crosses isn't a doorway, it's a region the particle is forbidden to occupy at all. It's a stretch of space where, by the classical rules, the particle simply cannot be. And yet the wave passes through it. So, does that passage take time? Does the particle linger inside the wall for some measurable sliver of a moment? Some tiny duration we could in principle put a number to? Or does it cross in no time at all, emerging on the far side in the very instant it entered, as if the wall's whole thickness meant nothing? Almost no time at all. That's the phrase in the title I've held back until now, and it turns out to be the most contested phrase in this entire corner of physics, because for nearly a century no one has been able to agree on the answer. Not because they lack the cleverness, and not because they lack the tools, you'll hear, in the parts still to come, about a clock built out of light itself, spinning fast enough to time events that last a billionth of a second, and about the microscope so sensitive it can feel a single atom by the whisper of particles leaking across an empty gap. The trouble runs deeper than instruments. The trouble is that the very question, how long did the particle spend inside a place it was never allowed to be, may be harder to answer than it first appears, harder even than it has any right to be. And that's where we're going. Rest here a while longer with the image of the sun, patient and warm. Each proton waiting its billion years to slip through the wall. Hold the seawall in your mind and the faint tremor on the sheltered side. And carry with you, softly, this one unanswered thing. The small mystery will follow all the way down into the quiet. Not whether the particle crosses, for we know that it does, but how long it takes to cross a wall it was never meant to enter at all. There is no rush to find out. The answer, or the beautiful lack of one, will keep. For now, let's simply linger in the strangeness and breathe and let the star burn slowly on. Let me stay with the wall itself for a moment, because the wall is where the whole story begins. Down in the core of the sun, two protons are trying to meet. And protons, you'll remember, both carry the same charge, the same positive sign, which means they push each other away. The closer they drift, the harder they shove back. It's the most ordinary thing in the world, the way two like charges refuse each other, the way you feel a faint resistance holding two magnets the wrong way round. But here that resistance rises into something enormous. Physicists call it the Coulomb barrier, a steep, invisible slope of repulsion that grows steeper the nearer the two protons come. A hill of pure electrical force standing between them and the fusion that would make them one. Now, the honest arithmetic of it is almost unsettling in its gentleness. 15 million degrees is the temperature of the sun's heart, and at that temperature the protons are flying, jostling, colliding at tremendous speeds. You'd think that would be more than enough. And yet it isn't. Not even close. Even at 15 million degrees, a proton simply does not carry enough energy to climb that hill of repulsion and reach the top. It races toward another proton, feels the slope steepen, slows, stops, and slides back down, turned away at the wall, again and again, like a wave that runs up a beach, only to be drawn back into the sea. By the plain rules of the world we can see and touch, the classical rules, fusion in the sun should almost never happen. The two protons should never touch. The star, by the letter of that law, should not shine. And here is the quiet miracle we've been circling toward. The proton does not climb the hill. It doesn't need to. It passes through it. To picture how, you have to let go softly of the idea that the proton is a tiny hardball with a single fixed place. In the deep quantum grammar of the very small, the proton is better described as a wave, a spread-out thing, a smear of possibility, a ripple of where it might be found. And when that wave meets the barrier, the wall of repulsion, it does not simply stop dead at the edge. Something subtler happens. The wave leaks into the forbidden region. Inside the wall, inside the place the proton has no classical right to be, the wave doesn't vanish all at once. It fades. It decays, smoothly, gently, growing fainter with every step deeper into the barrier. Physicists have a lovely word for a wave like this, evanescent, meaning fading, meaning vanishing, but not, crucially, meaning gone. Because if the wall is thin enough, the wave has not quite faded to nothing by the time it reaches the far side. A trace survives. A whisper of the original ripple emerges on the other side, into a place the proton could never have walked. And a surviving whisper of the wave means a real, honest chance, small, but never zero, that the proton is simply there, beyond the wall, as though the wall had let it slip clean through. That is the whole of it. Nothing bores a hole. Nothing tunnels in the way a mole tunnels through earth, though tunnelling is the name we've kept. What crosses is not a little digging particle, but the faint, leaking tail of a wave, the amplitude, the raw possibility, seeping through a barrier too thin to hold it fully back. The proton was never seen inside the wall, halfway through, caught in the act. It was on one side, and then, with a small and lawful probability, it was on the other. The sea-wall stood firm, and still a tremor reached the sheltered water beyond it. This is why the sun burns. Not by force, the protons never have the force, but by patience, and by leakage, and by the sheer number of tries. Deep in the core, protons meet and are turned away uncountable times over. But every so often, against all the odds of the classical picture, one wave's faint tail slips through another's, and two protons find themselves close enough to fuse. The reaction that follows has a rhythm to it, a chain, and it's worth walking down slowly, because each step is its own small event. The two protons that come together make at first the lightest possible union, but they cannot simply stay as two protons stuck side by side. For them to hold, one of the protons must quietly change its nature, must turn into a neutron, and that transformation is governed by the weakest of nature's forces, the one we call, plainly, the weak interaction. It is a slow, reluctant force, and it acts only rarely. So the fusion needs two improbable things at once: the tunneling through the wall and, in the very same instant, that grudging weak force conversion. Two rare events folded together. And when at last they do occur, what's left is deuterium, heavy hydrogen, a proton and a neutron bound as one, the first true rung on the ladder that lights the sky. There's a name for the narrow window where this all comes together, and it has a soft, almost welcoming sound, the Gamow peak. It marks a kind of compromise, a meeting in the middle. The very fastest protons, the ones with the most energy, are also the rarest. There are hardly any of them. The slower, common protons are everywhere, but they tunnel far less easily. Somewhere between those two facts lies a sweet spot, energetic enough that tunneling isn't hopeless, common enough that there are protons to spare. Fusion happens, overwhelmingly, in that gentle window of agreement. The star lives inside the Gamow peak. And now hold in your mind the strangest, most beautiful consequence of all this rarity. Because tunneling is so improbable, and because that weak force step is so reluctant, a single proton drifting in the sun's core will wait, on average, something like 1 billion years before it finally fuses. 1 billion years. Not a fraction of a second, not an afternoon, not a human lifetime, but a span of time that beggars the imagination, spent simply waiting for its improbable turn. And that unbearable slowness is not a flaw in the sun. It is the reason for the sun. If fusion were easy, if protons leapt the wall the moment they met, the sun would have spent all its fuel in a brilliant brief flare and gone dark long before there was anyone here to look up at it. The very difficulty of the crossing is what stretches the star's life across billions of unhurried years. The wall that should have stopped the sun from shining is, in the end, exactly what lets it shine so gently, and for so long. There's a self-correcting grace in it, too, a kind of built-in calm. Because tunneling is so exquisitely sensitive to temperature. Because a small rise in heat swells the fusion rate, and a small fall shrinks it, the sun holds itself steady without any hand to guide it. Fuse a little faster, and the extra warmth pushes outward, and the core swells the smallest amount, and swelling cools it, and cooling slows the fusion back down. A star breathing against its own weight, minding itself, needing no keeper. The throttle on all that living fire is nothing more dramatic than the quiet statistics of waves leaking through a wall. So we know that the crossing is real. We know it in the plainest possible way, by the warmth on your face on a bright day, by the fact that there is a day at all. The particle passes the barrier it cannot climb, and the passing lights a star. And the star has burned patiently for ages, and will burn on for ages more. That much is settled, textbook, beyond dispute. But settle back now, because there's one thing about that crossing we have not touched. One small question left lying in the dark, and it is the question that has refused to close for nearly 100 years. The proton slips through the wall. Fine, we've made our peace with that. But while it was inside the forbidden thickness, inside the place it had no right to be, how long was it there? A moment? No moment at all? And who could ever hope to hold a clock to a thing that lasts less than the blink of an eye? That question can wait a little while longer. Let it rest at the back of the room, patient and soft. Because before we can answer it, before we even begin to describe the clocks that were built to try, we need to understand just how ruthless the wall really is. Not in the way of something frightening, but in the way of something exact. The tunneling we have been speaking of does not happen because the rules are loose. It happens in spite of rules that are almost impossibly strict. And the strictness is worth sitting with, because it is the same strictness that explains almost everything else we are going to find tonight. The barrier does not treat all particles equally. It has a preference, and that preference is expressed in a single mathematical fact that runs through every story we will tell. The probability of tunneling falls off exponentially with the thickness of the wall and with the square root of the particle's mass times the height of the barrier above the particle's energy. Exponentially, that word is doing a great deal of work, and it deserves a moment of unhurried attention. You have probably heard exponential growth described in ways that make it sound impressive, a doubling that keeps doubling, a number that climbs a staircase and then suddenly seems to leave the staircase behind. Exponential decay is the mirror of that, and it is at least as striking. When something falls off exponentially, it does not merely halve when you double the relevant quantity. It can fall by a factor of 10, 100, 1,000, or more. Double the barrier's thickness, and the tunneling probability does not simply drop to half. Depending on the particle and the barrier, it might fall to 1/100th of what it was, or 1/1,000,000th. The wall becomes not twice as hard to pass, but immeasurably harder. Think of it like sound moving through stone. Press your ear to a thin wall, and you might catch, faintly, a voice on the far side. Press it to a wall twice as thick, and you hear almost nothing, not half the sound, but something far closer to silence. The sound does not merely dwindle, it is swallowed. That is an imperfect comparison, but the texture of the steepness is right. The quantum wall is steep in exactly that way. And yet, and this is the quiet miracle that the whole of tonight rests on, not quite zero. The amplitude of the wave function does not reach zero. It decays and keeps decaying, and if the wall is thin enough, a faint but real remnant survives on the far side. Not a large remnant. In most circumstances, a very small one, but non-zero, and that distinction between vanishingly small and precisely nothing is the entire story. There is an image that has been with me since we began, one that I keep returning to because it holds something true about all of this without requiring any mathematics at all. Imagine a wave on the sea, a long, low swell rolling in off open water, meeting a stone wall that extends down from the surface. Most of the wave reflects. You can watch it, the wall pushing back against the water, the crest folding backward on itself, retreating the way it came. But the wall is not perfectly sealed to the seabed. There is a gap at the bottom, narrow and dark, and a small disturbance makes it through, not a wave in the full sense. Not the rolling energy of the original crest, but a faint motion, a ripple, a lapping that can just barely be felt on the far side. Thin enough wall, quiet enough measurement, and something is there. The particle is the wave. The far side ripple is the escaped probability. The seawall is the barrier. And what makes it through is not a copy of what came in. It is small. It is diminished, but it is real, and real is enough. The size of the ripple depends exquisitely on the thickness of the wall. In the quantum case, that sensitivity is not merely strong, but staggering. The tunneling probability relevant to electrons crossing atomic scale gaps in something like a nanometer can be enormous by the standards of the effect. The tunneling probability for a proton, heavier and slower, is far smaller but still consequential, as we have already seen in the Sun's core. And for something with the mass of a tennis ball crossing a wall of any sensible thickness? The ripple is so inconceivably faint that it would not stir once in any imaginable span of time. The universe is old, but not nearly old enough. So tunneling is not a loophole in nature, it is a precise and narrow slot, carved by the mathematics of mass and energy and thickness, and only certain things fit through. The mass dependence is a point worth staying with for a moment, because it has a quiet elegance. Lighter particles tunnel better than heavier ones, at the same barrier and the same energy. Electrons, light, fast, barely there in terms of mass, tunnel almost casually compared to protons. Protons tunnel compared to whole atomic nuclei only when conditions are extreme, as in the Sun's core. And a whole atom tunneling as a unit is something that almost never happens, confined to very special situations. The scale of the mass is what determines the scale of the crossing. This is why quantum tunneling is a world of the very small, why it belongs to electrons and protons and not to rocks and rivers. Now, all of this was understood not from the beginning, not from the early days of physics, but from a particular moment that came quite suddenly after the new mechanics arrived in the mid-1920s. Quantum mechanics, the mathematics of wave functions, of probability amplitudes, of all the strange and gentle rules that govern the world at atomic size, came together rapidly between 1925 and 1927. And almost immediately, before the ink on the new equations was dry, people began noticing a consequence that nobody had fully expected. Friedrich Hund was one of the first to see it in 1927, and he saw it not in something exotic, but in something as ordinary as the smell of ammonia. The ammonia molecule, nitrogen flanked by 3 hydrogens, has a shape like a shallow umbrella, with the nitrogen at the top and the 3 hydrogens spread below it. And Hund noticed something strange in the molecule's spectrum. Something in the way it absorbed and emitted light that implied the nitrogen atom was flipping, moving from one side of the hydrogen plane to the other, passing through the molecular barrier as though the barrier were thin enough, under the right conditions, not to stop it entirely. This was called inversion, the ammonia inversion, and it is still discussed in chemistry courses today. The nitrogen does not climb over the barrier that separates the 2 positions, it passes through it, or rather its wave function amplitude leaks through it, and the nitrogen finds itself on the other side without ever having had enough energy to go over the top. Hund recognized this as the new wave mechanics in action. It was a quiet first sighting, a molecule flipping rather than a particle escaping, a spectroscopic line rather than a dramatic explosion, but it was there, unmistakably, in the data. The following year, 1928, brought something louder. Radioactive decay had been understood as a fact for decades by then. Certain elements shed particles and energy, transforming themselves into other elements. And this transformation happened on timescales that ranged bewilderingly from fractions of a second to billions of years. The pattern was named the Geiger-Nuttall law, after the experimenters Hans Geiger and John Nuttall, who had mapped it in 1911, but the pattern was a description, not an explanation. Why did some nuclei decay in microseconds and others endure for an age of the world? Why did the energy of the emitted particle matter so much to the decay rate? No one knew. alpha decay was the clearest puzzle. An alpha particle, two protons and two neutrons locked together, the nucleus of a helium atom, emerges from a heavy radioactive nucleus with a characteristic energy. That energy is always far below what you would need to have simply climbed out over the barrier that the nuclear force builds around the nucleus. The nuclear force holds the contents of a nucleus together so tightly that the barrier it creates is enormous, far too tall for an alpha particle to surmount from inside. And yet, the alpha particle leaves. It leaves reliably, reproducibly, at energies that are, by the logic of classical physics, completely insufficient for the job. George Gamow, a young Ukrainian physicist working in Göttingen, solved this in 1928. And quite independently, in the same year, Ronald Gurney and Edward Condon solved it separately in a paper published in the United States. The alpha particle, they understood, does not climb the barrier. It tunnels through it. Gamow's calculation was elegant in the way the best physical insights tend to be. It used the new quantum mechanics in the most direct way possible, took the exponential decay of the wave function inside the barrier seriously, and came out the other side with a prediction. And the prediction matched. Not just qualitatively, not just in the rough shape, quantitatively, the half-lives, the energies, the whole bewildering span of the Geiger-Nuttall relationship came out correctly. A nucleus that emitted alpha particles at slightly higher energy had a shorter half-life, and the relationship between the two was exponential. Not linear, not proportional, exponential. This is where the quiet power of the exponential rule becomes, for a moment, genuinely astonishing. Tiny changes in energy produce enormous changes in half-life. We are not talking about small differences here. We are talking about a range that spans, in the elements that undergo alpha decay, from about a microsecond on the short end to timescales measured in billions of years on the long end. The same basic physical process, an alpha particle tunneling through the nuclear barrier, accounts for both extremes. The difference is in the energy and the sensitivity of the tunneling probability to that energy. Consider what that means. A nucleus whose alpha particle has just a little more energy than another's will decay far faster, not twice as fast, not 10 times as fast, but potentially billions of times as fast. And a nucleus whose alpha particle has slightly less energy will endure for billions of years, sitting quietly, waiting. The exponential wall does not merely separate fast from slow. It creates a span of timescales so wide it encompasses, on one end, objects that would vanish before you could blink, and on the other end, objects that have survived since before the Earth was formed and will survive long after it is gone. The Geiger-Nuttall relationship had been an empirical fact for 17 years when Gamow, Gurney and Condon gave it a mechanism. Now it was understood. The shorter the half-life, the higher the particle's energy, the thinner the effective barrier at that energy, and the stronger the tunneling probability. The longer the half-life, the lower the energy, the thicker the barrier, and the weaker the leakage. It is a single mechanism stretched over an almost incomprehensible range. There is something very calming in that, once you let it settle. The same physics that explains why one nucleus vanishes in a flash also explains why another sits unchanged for an eon. Nothing different is happening, no different forces, no different laws, just the same exponential rule, applied at slightly different energies, producing differences that feel almost categorical, but are actually continuous. A spectrum. A quiet, patient, mathematical spectrum. Now here is a way to hear this, not just think it. You may have encountered a Geiger counter, that handheld device with its distinctive ticking, each click a small percussive sound in the quiet of a room. If the counter is measuring a material that undergoes alpha decay, then each of those clicks is the record of a single alpha particle that has made it through the nuclear barrier. Each click is tunneling made audible. Not in some metaphorical sense, not as a useful teaching illustration. Literally, the physical process generating that sound is an alpha particle that crossed a classically forbidden region by wave function leakage, that reached the detector by a route it had no classical right to take, and the click is the electrical pulse its arrival caused. Listen to a Geiger counter near a radioactive source sometime if you ever have the chance, and let yourself think about that for a moment. The rhythm is irregular, as it should be. Quantum processes are inherently probabilistic, not scheduled, but each individual sound marks one event, one successful crossing. The counter does not click for particles that reflected, only the ones that made it through. And over any span of time, the rate of those clicks follows precisely the exponential curve that Geiger and Nuttall described and that Gamow explained. The statistics of quantum amplitude decay, expressed as sound. It is a gentle thing to contemplate late in the evening. All those small crossings, each one the outcome of a wave lapping through a gap, arriving as a click, tunneling, made audible. The invisible, made briefly heard. Gamow's insight opened a door that turned out to be very wide. Alpha decay was the first clear case in nuclear physics, but tunneling did not stay in the nucleus. As the 20th century moved forward and electronic technology developed, as transistors and semiconductors became the foundation of a new world, the same exponential leakage that Gamow had described in atomic nuclei began to show up, in one form or another, nearly everywhere physicists and engineers looked. The next time tunneling stepped clearly into view was in the mid-1950s and into the late 1950s, when a young Japanese physicist named Ryo Esaki, working at a laboratory in Tokyo, began pressing a very thin semiconductor junction to unusual limits. Esaki was exploring what happened when you took the doped semiconductor materials that transistors are made of and made the junction between them, the boundary layer extremely narrow and the doping extremely heavy. The intuitive expectation would have been that the current through such a junction should behave in a predictable, smooth way, rising as the voltage rises, falling as it falls. What Esaki found instead was stranger. At low voltages, the current actually decreased as the voltage increased. The junction conducted better at low voltages than at somewhat higher ones, before settling into normal behavior at still higher voltages. This negative resistance, current falling as voltage rises, was unexpected in a device that was supposed to behave like an ordinary diode. Esaki recognized it as the signature of electron tunneling through the thin junction barrier. The electrons were not climbing over the gap between the two semiconductor regions, they were leaking through it, tunneling, and the quantum statistics of that leakage created the anomalous current versus voltage curve that no classical theory predicted. This device became known as the tunnel diode, and it was fast. Because tunneling does not require the particle to accumulate classical kinetic energy or overcome a thermal barrier, tunneling-based switching can happen extraordinarily quickly. The tunnel diode could switch states far faster than conventional transistors of its era. It found applications in high-frequency oscillators and in microwave electronics, in fast logic circuits, and in other places where speed was more important than almost anything else. Around the same time, a Swedish physicist named Ivar Giaever was working on the properties of superconductors, materials that, below certain very cold temperatures, carry electrical current with no resistance at all. Gieva became interested in what would happen if you sandwiched a very thin insulating layer between two superconductors. The insulating layer was a barrier. Classically, electrons from one superconductor should not be able to cross it. But Gieva tested what tunneling might do here, measuring the current that flowed between the two superconductors as a function of the voltage across the thin, insulating gap. The results showed, clearly and measurably, that electrons were tunneling across the barrier, and the pattern of the tunneling current as voltage changed gave precise information about the energy states of the superconducting electrons, their so-called gap, the energy it cost to break apart the paired electrons that carry supercurrent. Gieva had made tunneling into a spectroscopic tool, a way of reading the interior energy structure of a superconductor from the outside, by watching electrons tunnel through a thin insulating wall. It was a precision measurement, not of the tunneling itself, but of what the tunneling current revealed. The barrier had become a kind of window. Then came the prediction that, in some ways, surprised even the experts. In 1962, a graduate student at Cambridge University named Brian Josephson was working on his doctoral thesis under the supervision of the theorist Philip Anderson, who was himself visiting from Bell Laboratories. Josephson was thinking about Gieva's tunneling setup, but pushing it further. In Gieva's experiment, individual electrons, unpaired, single electrons, tunneled through the insulating barrier. But in a superconductor, the current is carried by something more complex, Cooper pairs, pairs of electrons that have coupled together through a subtle interaction with the crystal lattice of the metal, moving in concert, sharing a quantum state. The question Josephson asked was this: could Cooper pairs tunnel through the insulating barrier as a unit? Not the individual electrons, but the bound pairs. The answer his calculation gave was yes, and it came with a set of predictions remarkable enough that some senior physicists initially doubted them. Josephson predicted not just that paired electron tunneling would occur, but that it would produce effects that had no classical parallel. A supercurrent, a current without resistance, could flow through the insulating junction even with no voltage applied, driven purely by the phase difference between the quantum states of the two superconductors on either side. Apply a steady DC voltage across the junction, and the current would not stay constant but would oscillate, producing an alternating current at a frequency that depended with exquisite precision on the voltage and on fundamental constants of nature. The junction would oscillate at a rate of about 483 MHz per microvolt of applied voltage. These became known as the Josephson effects, and they were, after some initial skepticism, experimentally confirmed. The precision of the relationship between voltage and frequency in the Josephson effect turned out to be so reliable that it became the basis for a metrological standard, a way of defining and measuring voltage with extraordinary accuracy. Josephson junctions are now used in the most sensitive magnetometers ever built, in certain kinds of quantum computing hardware, and in the voltage standards that calibrate electrical measurements worldwide. All of it, ultimately, resting on the fact that quantum wave function amplitudes do not stop at a barrier. In 1973, the Nobel Prize in Physics was shared among 3 researchers whose work had, each in its own way, demonstrated the consequences of tunneling in solid materials. Leo Esaki received it for the tunnel diode, the negative resistance device he had found by pressing semiconductor junctions to their limits in the late 1950s. Ivar Gieva received it for the tunneling spectroscopy of superconductors, for turning the thin insulating barrier into a window through which the energy states of a superconducting material could be read. and Brian Josephson received it for his theoretical prediction of paired electron tunneling for the Josephson effects that gave metrologists a new tool and gave quantum engineers a new building block. 3 prizes in one, from a phenomenon that had been barely a theoretical curiosity in 1928. By 1973, tunneling was not just a laboratory oddity or a way of understanding radioactive decay. It was an engineering resource, a metrological foundation, something built into devices that were quietly and already becoming essential to modern life. And there is an additional layer here that is worth a slow, appreciative thought. The tunnel diode was fast, because tunneling is not slowed by thermal activation, not waiting for a particle to gather enough classical kinetic energy to climb a hill. Josephson junctions are precise because the tunneling current depends on phase differences between quantum wave functions, and phase is a quantity quantum mechanics can define with a clarity that classical quantities can rarely match. The STM, which we will come to shortly, is sharp because the tunneling current changes so steeply with distance by roughly a factor of 10 for every angstrom, every tenth of a nanometer. In each case, the engineering value of tunneling comes from the same mathematical property that makes the exponential wall so strict in the first place. The steepness that seems like a barrier is also, from the right side, a lever. This is one of the quieter pieces of beauty in the story of the effect. The same mathematical sensitivity that keeps the tennis ball on one side of the wall forever, that makes tunneling so vanishingly rare for macroscopic objects, so confined and so precise for atomic scale particles, is what gives the scanning tunneling microscope its ability to resolve a single atom's height, what gives the Josephson junction its voltage to frequency precision, what makes the Geiger counter's clicks a reliable record of individual events rather than a statistical blur. The strictness and the usefulness are the same thing, seen from different angles. We have travelled in this part of the story through 3 decades and several Nobel Prizes, through the nucleus and the solid-state device and the superconducting junction. And the thread connecting all of it is the same quiet, steep, exponential leakage of wave function amplitude through a barrier that no classical particle can cross. Gamow found it in the nucleus in 1928, explaining why a clock-like regularity had been hiding in the chaos of radioactive decay. Esaki found it in the semiconductor in the late 1950s and built a device from it. Gieva found it in the superconducting junction. Josephson predicted it in paired form from an armchair calculation that turned out to be entirely correct. By the early 1970s, then, tunneling was established, confirmed, put to work. It had been turned into devices. It had been given Nobel Prizes. It was textbook physics, graduate level but settled, not a speculation, not a fringe. And yet, and here is the thread we have been carrying, the question that was set down gently at the close of part 1, and has been resting at the edge of the room all this while, there was one thing about the tunneling event that none of these confirmations, none of these Nobel-winning demonstrations had actually answered. The devices worked. The half-lives matched. The clicks were heard, but no one had measured what happened inside. Inside the barrier, in the classically forbidden region, the place the particle had no right to be, time was not a quantity anyone had successfully attached to the crossing. Not because they hadn't tried. Not because the question had been overlooked or forgotten, but because the question, as it turned out, was harder than it looked. Harder even than building a device out of paired electrons tunneling through an insulating junction. Harder perhaps, than explaining why the sun shines. Because the barrier is not just a wall in space, it is a wall in the space of what quantum mechanics permits you to know. Once you ask how long a particle lingered in a place it wasn't supposed to be, you are asking the wave function to give you information it does not, in the standard picture, carry cleanly. You are asking for a trajectory through a region where no trajectory exists, a watch reading from a particle that was never, while inside, a localized thing. This is the question we have arrived at, the one that waited patiently while we were learning the exponential rule, and the history, and the Nobel Prizes. How long, and who, if anyone, could hope to answer it? The answer required a clock that did not yet exist, a clock not made of gears or crystals or atomic oscillations in the usual sense, but something stranger, a clock made of light itself, spinning, and that clock had a name. It was called the attaclock, and it was built, eventually, from pulses of laser light so brief that describing their duration requires a number so small it seems to dissolve the idea of duration altogether. To understand what the attaclock is, and why it was needed, and what it found that it couldn't quite settle, we need first to let that number land properly. Not to rush past it, but to sit with it the way you might sit with the size of the ocean, letting the scale come in slowly at the edges of what you can hold. An attosecond is 10 to the power of -18 seconds. Written out, it is a decimal point followed by 17 zeros followed by a 1. It is a billionth of a second. To describe it another way, an attosecond is to 1 second what 1 second is to the entire age of the universe. Not a piece of the age of the universe. Not a fraction of a billion years. The age of the universe, from its beginning to now, is roughly the same multiple of a second as a second is of an attosecond. Let that be quiet for a moment. Let the scale simply be what it is. The motion of electrons inside atoms, the way they respond to the electric field of a laser pulse, the way they rearrange themselves during a chemical reaction, the way they shift when light strikes a surface, all of this happens on the time scale of attoseconds to a few femtoseconds, a few thousandths of a trillionth of a second. This is the natural clock of atomic scale electron dynamics. And if the crossing of a tunneling barrier, if whatever time the particle spends inside the classically forbidden region, is a real and finite duration, it is a duration that lives somewhere in this range. Not hours, not seconds, not even microseconds, attoseconds or femtoseconds at the longest. For most of the 20th century, no tool existed that could resolve events at this scale. It was not a technological gap that was expected to close soon. It was a gap that seemed, for a long time, fundamental, a floor below which measurement simply could not go. Not because of engineering limitations, but because of something deeper about how light and matter interact. And then, in the decades leading up to the early 2000s, that floor began to crack. The floor began to crack, not all at once, but through a slow accumulation, patient work by many hands across many years, laser physics refined by increments, optical methods handed from one generation of researchers to the next, each slightly sharper than before. Before we arrive at those tools, though, before we follow the physicists who built a clock out of light to time a crossing that may take no time at all, it is worth pausing at an earlier instrument. One that does not attempt to time the crossing. One that simply feels it, the way a hand pressed against a thin wall might feel the warmth of a fire on the other side, not seeing through. Not passing through, but sensing what is there through the thickness of what separates. This instrument proved, in a way that left no room for abstract objection, that tunneling is not a convenience of the mathematics. It is not a formal feature of the equations that somehow cancels out when you press your face close to the physical world. It is as real as the current flowing through a wire, as real as a needle lifted a fraction of a hair's breadth above a surface and held steady in the dark, as real as 3 letters spelled out, atom by atom, on a copper surface in a laboratory in California. The instrument is called the scanning tunneling microscope, and its story begins in Zurich. IBM's research laboratory in Rischlikon, just outside Zurich, was by the early 1980s one of the places in the world where fundamental physics was done with corporate resources and a freedom that most universities could not match. Gerd Binnig and Heinrich Rohrer worked there, 2 physicists whose collaboration had a quality of complementary instinct, one inclined toward the broad conceptual leap, the other toward the careful engineering of an idea into something that could actually be built and made to function. In 1981, they brought the scanning tunneling microscope to life, and what it did was so immediate and so concrete that it changed, in a practical and unrepeatable way, the meaning of the word see. The machine does not use light. This is the first thing to understand about it, and the thing that makes it so strange. Every microscope before it, every instrument that had ever allowed a human being to resolve the features of a surface below the wavelength of visible light, had relied on some form of radiation, light waves, X-rays, electron beams bent through magnetic lenses. The scanning tunneling microscope uses none of these. It uses a needle. The needle is not a needle in any conventional sense. It is a metal tip, tungsten, typically, or platinum iridium, that has been sharpened through electrochemical etching or simple mechanical manipulation until its apex terminates, ideally, in a single atom. A 0.1 atom wide at its end. The ideal is never guaranteed. Preparing a usable tip is something between a craft and a lottery, and experienced operators learn which preparation methods are more likely to produce a genuinely sharp apex, and which are more likely to yield a tip that gives blurred, uninterpretable signals. But when it works, when the apex is truly a single atom hovering above a conducting surface, what happens next is a direct, literal consequence of quantum tunneling. The tip is brought close to the surface. Not touching it, the whole point is that the tip never touches. The gap between the apex of the tip and the surface is roughly a nanometer, sometimes less. A nanometer is a billionth of a meter. It is an almost incomprehensible smallness in everyday terms. Yet in the language of atoms, it is a comfortable distance, roughly the span of 10 hydrogen atoms placed side by side, or the diameter of a moderately large molecule. At this distance, the gap between tip and surface is not filled with anything. It is vacuum, or as close to vacuum as can practically be achieved in a laboratory. There is nothing in between. Classically, that means no current should flow. The electrons in the tip have no path to the surface and no energy sufficient to leap the gap. The circuit is open. Nothing moves, except that it does. Because the gap is narrow enough, because the barrier it represents is thin enough in the quantum sense, electrons tunnel across it. They do not arc through the air, do not receive a boost of energy that somehow propels them from one side to the other. They simply appear on the far side in the way that a wave's influence can be felt through a thin partition even when no material passes. The probability amplitude leaks through, and with it comes a measurable current, the tunneling current. And this current is fantastically, almost unreasonably sensitive to the width of the gap it crosses. Here is the number that makes the scanning tunneling microscope possible. Close the gap by the width of a single atom, a change of roughly 1 angstrom, 1/10,000,000th of a meter. A distance so small it exists below the resolving power of any light-based instrument ever made, and the tunneling current increases by approximately a factor of 10. Open the gap by that same single atom width, and the current drops by roughly a factor of 10. 1 atom of height, 1 order of magnitude of current change. This exponential sensitivity is not a design achievement. It is not something the engineers built in. It is the direct consequence of the same exponential dependence that governs all tunneling. The tunneling probability falling steeply with barrier width, so that the tiniest change in distance produces a large change in outcome. Binnig and Rohrer did not invent this sensitivity. They recognized it and harnessed it. If you hold the tunneling current constant by continuously adjusting the tip's height as it moves across the surface, the record of those tiny height adjustments traces the topography of the surface, atom by atom. The bumps and valleys of a solid surface at the scale of individual atoms become a map you can read. In 1986, Gerd Binnig and Heinrich Rohrer received the Nobel Prize in Physics for this work, the prize shared with Ernst Ruska, the inventor of the electron microscope, as if to mark both the continuity and the break. Here is where the old way of seeing met the new. The Nobel Committee's description of the STM was, in its precision, almost quiet. It noted that the instrument could image individual atoms on a conducting surface, not clusters of atoms, not the statistical average behavior of a surface, individual atoms. The thing that had seemed, for most of the history of science, a metaphysical category rather than an observable fact, the single atom, became something you could point at. But even this achievement, extraordinary as it was, understates what the scanning tunneling microscope eventually made possible in the hands of those who came after Binnig and Rohrer. In 1989 and 1990, at IBM's Almaden Research Center in San Jose, California, a physicist named Don Igler and his colleague Erhard Schweizer did something that had never been done before in the history of matter. They used a scanning tunneling microscope, used the same tunneling current that Binnig and Rohrer had used to image surfaces, to move individual atoms, not to image them and leave them where they were, to pick them up, in a sense, and place them down again somewhere else, with the precision of a single atomic diameter. The surface was copper, cooled to 4 degrees above absolute zero to minimize the thermal jostling that would otherwise send atoms wandering on their own. The atoms being moved were xenon, a noble gas, chemically inert, chosen partly because its relative heaviness makes it more amenable to being nudged by a tunneling tip than lighter atoms, and partly because it sits on copper surfaces in a reliable and predictable way. The tip of the STM was positioned above a xenon atom. The tunneling current increased slightly, enough to create a small, attractive interaction between tip and atom without pulling the atom off the surface. And then the tip was moved laterally, dragging the xenon atom across the copper. Then the interaction was reduced again, and the atom stayed where it had been placed. They did this 35 times. 35 individual xenon atoms, moved one at a time, positioned on a copper surface with single atom precision. When the arrangement was complete and the STMs scanned back over what they had built, the image showed 3 letters, IBM, the logo of the company they worked for, spelled out in the smallest possible ink, atoms. Each one a blunt round bump in the topographic map the tunneling current drew. The image was published and became, in the strange way that certain scientific images do, something beyond a result. It became a demonstration, not of IBM's resources or the ingenuity of Eigler and Schweizer, though it was both of those things. A demonstration that matter at its most fundamental level is not an abstraction. It can be touched, shaped, arranged. The tools for doing so are made of tunneling. There is something worth sitting with in the image of those three letters. 35 xenon atoms. Each one placed by a current that flowed through a barrier it had no classical right to cross. Each one imaged by the same impossible current, reading back what had been written. The entire operation, the writing and the reading, depended on quantum tunneling from start to finish. Not as a theoretical support, not as a background phenomenon that could in principle be replaced by something classical. Tunneling was the mechanism. Remove it, and there is no image, no letters, no manipulation. Just a needle hovering in the dark above a surface it cannot see. The scanning tunneling microscope and its descendants, the atomic force microscope, the various near-field probe instruments that followed, represent tunneling in its most legible form. You can hold the result in your hands, or at least in your eyes. The IBM logo in xenon is a picture of tunneling consequences, crystallized. But tunneling does not wait to be invited into the visible and the celebrated. It works in places far less dramatic, in devices so ordinary that the word device barely applies anymore, because they have become infrastructure, become the invisible condition of modern life. The memory stored on a computer's hard drive or a phone's internal storage, the kind called flash memory, operates on tunneling. Flash memory stores information by trapping electrons on what is called a floating gate, a small conductor surrounded by an insulating layer, so called because it is electrically isolated from everything around it. To write a bit of information, a voltage is applied that is strong enough to force electrons through the insulating barrier and onto the floating gate, where they remain, held by the insulator on all sides, for years without power. To erase, a different voltage pushes them back the other way. In both directions, the electrons cross the insulating barrier not by climbing over it, but by tunneling through it. Every photograph on a phone, every document on a laptop, every film downloaded and held on a device through which no continuous power flows. All of it is written in electrons that crossed barriers by tunneling and read back by detecting whether those electrons are still on the other side. This is not a niche application. Flash memory is one of the most manufactured technologies in human history. Billions of chips produced every year, each containing billions of these floating gate cells. Each cell operating on the same principle that Gamow recognized in the nucleus of a radioactive atom. Alpha decay made the principle visible. The tunnel diode made it controllable in a semiconductor. The floating gate made it a commodity. But the same sensitivity that makes tunneling useful in the floating gate makes it troublesome elsewhere, and this troublesomeness is becoming. As the years pass, one of the central engineering problems of the semiconductor industry. Transistors, the switches that form the logic of every computing device, must insulate as well as conduct. A transistor that allows current to flow when it should be off is a transistor that wastes power, generates heat, and in the extreme case fails to compute correctly. The insulating layers inside modern transistors are thin. They have to be, because making transistors smaller requires making every dimension smaller, including the insulators. And as those layers thin toward the atomic scale, tunneling begins to occur across them even when the transistor is meant to be off. Electrons that should be blocked instead cross. invisibly, through barriers that are no longer quite thick enough to hold them. This leakage is not a design flaw in any particular chip. It is a consequence of the same physics that lit the sun and spelled IBM in xenon. The tunneling probability is exponentially sensitive to barrier width, and when the barrier narrows to the point where the exponential becomes favorable, electrons cross it regardless of the engineer's intentions. Every generation of transistors made smaller than the last runs deeper into this problem. The flaw is not quite the atomic flaw yet, but it is close enough that physicists speak seriously of fundamental limits, not engineering limits that better fabrication can solve, but physical limits set by quantum mechanics itself. On how thin an insulating layer can be before tunneling makes it useless as an insulator. So tunneling appears here too, not as a tool, not as a curiosity, but as a constraint. A wall the engineers are running into from the other side. There is one more place to find it, and this one requires the smallest shift in scale, not from the human to the atomic, but from the atomic to the biological. Inside every living cell, chemistry proceeds through a constant traffic of electrons and protons, passed from molecule to molecule, in reactions that extract energy from food, build and dismantle proteins, maintain the electrical conditions that allow a nerve to fire or a muscle to contract. Many of these reactions involve the transfer of a hydrogen atom, a proton, and its electron, from one molecule to another. And in certain enzymes, the proteins that act as catalysts for biochemical reactions, this hydrogen transfer happens faster than any classical thermal motion can account for. The reason, as careful measurement has shown, is tunneling. The proton, the lightest nucleus, the hydrogen nucleus, is heavy by electron standards, but still light enough, and the distances involved in enzyme active sites small enough that proton tunneling contributes measurably to the reaction rate in certain cases. Enzyme hydrogen tunneling has been measured in reactions catalyzed by alcohol dehydrogenase, by aromatic amine dehydrogenase, and by other enzymes whose names do not need to be remembered to appreciate what their behavior implies. The same quantum leakage that lets stars burn is at work inside the cells of your body, in the quiet of mitochondria, in the dark chemistry that turns the food you ate today into the motion of your breath. The sun tunnels protons. Enzymes tunnel protons. The mathematics is the same. The scale of consequence differs. One heats an entire solar system, the other assists a reaction that would take slightly longer without it, but the mechanism is not different in kind. Tunneling is not an exotic exception inserted into physics to explain one strange phenomenon. It is a structural feature of the quantum world, present wherever a barrier is thin enough and a particle light enough, from the nuclear to the biochemical to the technological. This is the picture that assembles itself as you hold all the examples together. The nucleus of a radioactive atom decaying on a timescale set by how far its alpha particle must tunnel. The core of the sun, fusing protons through a Coulomb barrier that classical temperature cannot surmount. The tip of a scanning tunneling microscope feeling a surface through a current no classical electron should carry. 35 xenon atoms arranged by the same current. Flash memory cells holding your files through electrons that crossed their barriers and stayed. Transistors thinned to the point where tunneling begins to leak through the walls meant to hold it back. And in the interior of living cells, enzymes whose hydrogen transfer reactions run partly on quantum probability. Across all of this, Tunneling is one thing, the leakage of a probability amplitude through a barrier that, classically, should be impenetrable. The wave function decays inside the barrier, but does not reach zero before the barrier ends, and so a small but real fraction of the probability appears on the other side, and the particle that fraction describes has crossed. Not by having the energy to climb over. Not by being pushed by an external force, simply by being described by mathematics that does not terminate where classical intuition says it should. And it is here, at this point, where the mechanism is established, where the reality of the effect has been demonstrated in forms ranging from a click of a Geiger counter to a logo spelled in atoms, that a question becomes unavoidable. A question that has been waiting, quietly, since the very first formal treatments of tunneling were written down in the years following 1928. A question that is simple to state and has proved, for nearly a century, astonishingly resistant to agreement. If the particle crosses the barrier, if it goes from one side to the other, how long does that crossing take? It sounds like a question with an answer. It sounds like the kind of thing that should have been settled within a few years of Gamow's 1928 paper. Refined perhaps as the mathematics matured, but essentially resolved by mid-century, there is a particle, there is a barrier with a definite width, there is a crossing. Duration equals distance divided by speed. We teach this to children. But the question, as it turns out, is not that question. The distance is there, the barrier has a width you can measure in nanometers or in atomic units, as precisely as you like. The crossing happens, you can detect the particle on the far side, that is not in doubt. What is missing is the part that connects them, the notion of the particle being somewhere inside the barrier at some time, moving through it, traversable by a clock. And what is missing not because no one has been clever enough to find it, but because quantum mechanics, as currently understood, may not provide it in the way the question demands. To see why, consider what it would mean to time the crossing. You would need to know when the particle entered the barrier and when it left. Knowing when something entered a region means knowing, at the moment of entry, where the particle was, at the leading edge of the barrier, and when it arrived there. Knowing when it left means similarly pinpointing its position at the exit edge. But the particle, inside the barrier, is not a classical object with a well-defined position. It is a wave function spread in space, decaying exponentially through the forbidden zone, but present throughout it in a probabilistic sense. To ask exactly when it entered and exactly when it left is to ask for two position measurements of exquisite precision in rapid succession, and quantum mechanics has a settled answer to what happens when you try to measure a particle's position precisely. You disturb it. You change it. The act of asking the question changes what the question is about. This is not a technical limitation. It is not that our detectors are too crude or our timing circuits too slow. It is that the question, where was the particle at time t1 and where at time t2, requires treating the particle as something that has a location inside the classically forbidden region, which is precisely what quantum mechanics does not provide. The wave function inside the barrier is a mathematical object that tells you the probability of finding the particle there if you look, but it does not describe the particle as being at a specific location, moving at a specific speed, traversing the barrier the way a billiard ball traverses a table. Physicists recognized this difficulty early. And in recognizing it, they attempted to get around it, to define some measure of tunneling time that could be extracted from the mathematics without requiring a continuous trajectory through the forbidden zone. Beginning in the late 1930s and continuing for decades, a collection of proposed definitions accumulated. Each one captured something real and was internally consistent. And each one, when placed next to the others, gave a different number. There is the phase time, sometimes called the Wigner delay time, or the Eisenbud-Wigner-Smith time. It tracks the delay experienced by the peak of a wave packet in passing through a barrier, comparing the transmitted wave to a freely propagating one. There is the dwell time, which asks how long the particle, averaged over all possibilities, spends inside the barrier region. There is the Lama time, which uses the precession of the particle's spin in a weak magnetic field applied to the barrier region as a clock. The spin rotates at a known rate, so the angle it rotates through inside the barrier gives a measure of how long the particle spent there. There is the Bittiker-Landauer time, which treats the traversal differently again, considering the timescale over which the barrier's properties can be modulated before the tunneling changes character from static to dynamic. These are not small technical variations on a single idea. They represent genuinely different physical questions dressed in the language of a single question. The phase time asks about the group delay of a wave packet's peak. The dwell time asks about the spatially averaged probability density over time. The Lama time asks about spin rotation as a proxy for duration. The Bittiker-Landauer time asks about the frequency at which the particle samples the barrier's static properties. They do not simply disagree about the number, they disagree, implicitly, about what tunneling time means. And among these definitions, one result attracted particular attention and particular concern. It was called the Hartmann effect, after Thomas Hartmann, who noted it in the early 1960s while working with the phase time. The Hartmann effect is this: for a sufficiently thick barrier, the phase time stops increasing with the barrier's width. The transmitted wave packet's delay saturates, make the barrier twice as thick, and the apparent traversal time does not double, does not even increase proportionally, it approaches a constant. Which means that for thick enough barriers, the implied traversal velocity can become arbitrarily large, which means, if you take the phase time as the actual traversal time, that a particle can seem to cross a thick barrier faster than light would cross the same distance in vacuum. This is the result that gave rise to the popular claim that tunneling is superluminal, that the particle, in crossing the barrier, outruns light. And it is a claim that carries an almost irresistible appeal. It has the flavour of the genuinely strange, the genuinely impossible, suddenly made real. It appears in popular accounts of quantum mechanics with a regularity that suggests it has become a kind of signature story, the moment at which physics reveals itself to be stranger than fiction. The difficulty is that it is not what is actually happening. The reconciliation is careful and important, and it depends on understanding what the phase time is actually measuring. A wave packet, a localized pulse of quantum probability, is not a single wave of definite frequency. It is a superposition of many frequencies, each of which passes through the barrier with a slightly different phase shift. The phase time tracks the delay of the peak of the transmitted packet relative to a freely propagating packet, and this peak is shaped by the interference of all those frequency components. In the regime where the Hartmann effect operates, what is happening is not that anything physical is travelling faster than light. What is happening is that the shape of the transmitted wave packet is being restructured, the leading edge of the incident packet is transmitted preferentially, and the peak of the transmitted packet therefore appears to advance earlier than you might expect. But no signal, no information, no energy, no causal influence is propagating faster than light. The peak arrived early because the packet was reshaped, not because anything outran causality. The mainstream resolution of the superluminal tunneling question is precisely this: pulse reshaping, not signaling. The peak of a pulse and the leading edge of a signal are not the same thing. Causality is protected. Relativity holds. The tunneling particle does not break the speed limit. The apparent violation dissolves when the phase time is correctly interpreted as a property of wave packet reshaping rather than as the actual transit time of a physical thing. But here is the complication. This resolution, though broadly accepted, does not resolve the underlying question. It tells you what the Hartmann effect is not. It is not faster than light signaling, but it does not tell you what the actual traversal time is, because it reveals that the phase time may not be the right quantity to use in answering that question. The resolution clears the field of a misconception, but it does not fill in the answer that remains. So the question persists, not because physicists forgot to look, and not because the mathematics is intractable, but because the question, posed in the natural way, rubs against the grain of what quantum mechanics describes. A century of attempting to time the crossing has produced a forest of definitions, a range of numbers that depend on which definition you use, and a genuine, unsettled argument at the frontier of experimental physics about which, if any, of these quantities measures something that could meaningfully be called the time the particle spent inside the barrier. This is the question the Atterclock was built to address. Not a thought experiment, not a theoretical revision, not a new mathematical framework, an experiment, an actual physical measurement designed with extraordinary ingenuity to extract, from the behavior of real particles in a real laboratory, a number that might correspond to the duration of the crossing. To build such an experiment, you need first to understand what attosecond means not just as a number, 10 to the power of negative 18 seconds, as small relative to a second as a second is to the age of the universe, but as a practical toolkit. Because the frontier of attosecond physics is not simply the frontier of very small time. It is the frontier of what can be done with light made strange, light compressed into bursts so brief they last fewer oscillations of the electromagnetic field than you can count on one hand. Light whose properties can be sculpted and shaped to interact with matter on the timescale of electron dynamics. An attosecond pulse of light is shorter than the period of a visible light wave, which lasts roughly 2 femtoseconds, 2/1000ths of a trillionth of a second. An attosecond pulse fits inside a single oscillation of visible light the way a single heartbeat fits inside an hour. Producing such a pulse requires inducing a high harmonic generation process in a noble gas, driving atoms with an intense infrared laser so that electrons are partially ionized and then recombine, emitting extreme ultraviolet light in bursts that can be as short as a few tens of attoseconds. The physics of this process was worked out theoretically and experimentally over the 1990s and into the early 2000s, and the three physicists whose contributions to it were most foundational received the 2023 Nobel Prize in Physics: Pierre Agostini of Ohio State University, Ferenc Krauss of the Max Planck Institute of Quantum Optics and Ludwig Maximilian University in Munich, and Anne Lewillier of Lund University in Sweden. The Nobel Committee's description of their work emphasized that attosecond pulses give humanity, for the first time, the ability to study electron dynamics in real time, to watch electrons respond to light rearranged during chemical reactions, and shift across molecular bonds on the timescale at which those events actually happen. Before attosecond pulses existed, such dynamics could only be inferred from the results of processes that were already complete. After attosecond pulses, they could be probed directly, with a temporal resolution finer than the events themselves. And so the question of tunneling time, the question that had sat unresolved for decades, the question that seemed too quantum to be answerable by any classical measurement, entered the attosecond era with a new possibility. Not certainty of answer, not a guarantee that the right experiment would close the debate, but a genuine experimental window where none had existed before. A tool fine enough that what it found might at last constrain what theory alone had left open. The specific instrument built to look through that window is called the attoclock. And the reason it is called a clock is that it uses a rotating laser field in the same way that an analog clock uses a rotating hand, not to display the time, but to encode it as an angle. To understand how it works and why it is clever enough to deserve the name, and what it has found, and why what it has found is still being argued over, that is where the next hour of darkness takes us. The question has been with us for nearly a century. The clock for answering it has existed for less than 2 decades. The attoclock begins with a laser. Not the familiar red dot of a pointer or the cutting beam of an industrial tool, but something stranger. A pulse of light so brief that it contains only a few oscillations of the electromagnetic field, and so intense that when it strikes an atom, it doesn't just illuminate the atom, it distorts it. It bends the space around the electron the way a strong current bends a riverbank, tilting the potential landscape until the barrier holding the electron inside the atom becomes thin enough, just barely thin enough, that the electron can slip through. This is strong field ionization, the quantum analog of prying open a door not by turning the handle, but by pressing the whole frame until the gap at the edge is wide enough to squeeze through. The laser's electric field adds its own slope to the atom's potential, the way a strong wind pressing against a wall makes the wall itself feel. To something small enough, as though it has a lean, a tilt, a direction of least resistance. On the side where the field pushes downward, the barrier the electron faces is lower and thinner. On the other side it is higher and thicker. The electron, described always as a wave function that decays exponentially inside the barrier rather than stopping at its face, leaks through the thin side. It tunnels out. And this happens not over minutes or seconds or milliseconds, but in a time that might be measured in attoseconds, if it can be measured at all. What makes the attoclock clever is not the laser alone, but the shape of that laser's polarization. A standard laser pulse oscillates in a single plane. Its electric field swings back and forth along one axis like a pendulum. A circularly polarized laser field does something different. Its electric field vector rotates continuously in a plane perpendicular to the direction the light is traveling, tracing a circle rather than a line. At any given instant, the field points in some direction. A fraction of a laser cycle later, it points in a slightly different direction. And a cycle after that, it has come all the way around. The field sweeps through all directions in space, the way a clock hand sweeps through all hours on a face, completing a full rotation once per laser period, which at optical frequencies means on the order of every 2 or 3 femtoseconds. Now here is where the clock idea becomes beautiful. If an electron tunnels out of the atom, it does so in response to the electric field at the moment it exits. The field at that moment points in some direction. When the electron emerges into free space on the far side of the barrier, that rotating field immediately begins to push the electron sideways, accelerating it and the direction in which the electron ultimately flies away. The direction in which it arrives at a detector encodes the direction the field was pointing when the electron came out. The final angle of the electron's departure is a record of the moment it emerged, the same way the position of a clock hand, when you glance at it, tells you the time. This is angular streaking. The rotating laser field is the hand. The electron's final angle is the reading. And if there is any delay between the moment the field first creates a thin enough barrier and the moment the electron actually emerges on the far side, that delay will show up as a small rotation of the electron's exit angle, a small discrepancy between where the hand was pointing when the barrier opened and where it was pointing when the electron came out. The rotation is the clock's record of how much time passed during the crossing. A larger delay means a larger angular offset. No delay means no offset. The electron comes out exactly where the instantaneous tunneling picture would predict. A measurable offset means the electron took a detectable, non-zero amount of time to cross the barrier that classically it should not have been able to enter at all. The attaclock, in other words, converts a time, a duration that might be shorter than a single oscillation of visible light, into an angle. And angles, unlike attosecond durations, can be measured with precision. You do not need a stopwatch faster than an attosecond to read the attaclock. You need a detector sensitive to direction, and a very careful accounting of everything else that might rotate the electron's path on its way to that detector. That last requirement is where the difficulty lives. The electron does not emerge into empty space. It emerges into the tail of the atom's own electric field, the Coulomb field of the nucleus it has just left. As the electron moves away from the atom after tunneling, the nucleus pulls back on it, deflecting its trajectory slightly. This Coulomb deflection mimics, in its effect on the final angle, exactly what a tunneling delay would produce. So if you measure the final angle and find it offset from the naive prediction, you cannot immediately say whether the offset comes from a real tunneling delay or from the Coulomb tug on the exiting electron, or from some mixture of the two. Separating these contributions requires theoretical modelling, and the models, it turns out, are not all the same. This is not a flaw in the experiment. It is the experiment's central challenge, the thing that keeps the attaclock from being a simple meter that you read and report. Every attaclock group has had to solve the problem of the Coulomb correction, to subtract out the deflection due to the atom's own field in order to isolate whatever remains as a genuine tunneling signature. And different groups, using different theoretical approaches to that correction, have arrived at different answers. Ursula Keller and her colleagues at IBM Zurich were among the first to develop and systematically apply the attaclock technique, beginning work in this area from around 2008 onward. Their experiments used noble gas atoms, helium and argon in particular. These are well-characterized systems, theoretically tractable, experimentally clean. The circularly polarized laser pulses were intense enough to ionize the atoms by strong field tunneling, brief enough that the rotating field served as a reliable clock hand, and the electron momentum distributions were measured with high precision. When Keller's group analyzed those distributions, applying their best theoretical models to account for the Coulomb correction and other effects, the results were consistent with a tunneling delay compatible with zero within their experimental uncertainty, or, at the very most, with a delay so small as to be indistinguishable from zero given the precision they could achieve. Their reading of the atoclock was, the hand barely moves while the electron crosses, near instantaneous, or as close to it as the measurement could resolve. That finding attracted enormous attention. It seemed to offer experimental grounding for the intuition that tunneling, in some meaningful sense, is not a process that unfolds in time the way a ball rolling down a ramp unfolds in time, but rather an all-at-once quantum event, a transition from one side to the other without a traversal in between. For a question that had been open since the 1930s, the idea that experiment had at last weighed in, even provisionally, was significant. The atoclock results from Zurich rippled through the community, prompted new theoretical work, and inspired other groups to build their own versions of the apparatus and try the measurement themselves. But here is where the story resists the tidy ending, because other groups and other approaches did not all arrive at the same place. In 2019, a study led by Synod and colleagues attempted what might be called the cleanest possible version of the atoclock measurement. Instead of helium or argon, atoms for which the exact potential is known but still involves multiple electrons interacting with one another, introducing small but real theoretical uncertainties, they used atomic hydrogen. Hydrogen is the one atom in all of quantum mechanics that can be solved exactly. The Schrödinger equation for hydrogen has a closed-form solution. There is no ambiguity in its potential, no electron-electron interaction to approximate, no model-dependent uncertainty in how the atom responds to the laser field. If you can do the atoclock experiment on hydrogen and account correctly for the Coulomb deflection, you have removed the theoretical slippage that allowed competing groups to reach competing conclusions. Hydrogen is, in a sense, the experiment's final appeal to exactness. The 2019 result, published in Nature, was read by its authors as consistent with no measurable tunneling delay. Their measured angular distributions, after applying the theoretical Coulomb correction appropriate for hydrogen, did not show an offset attributable to a finite traversal time through the barrier. The electron appeared to emerge as though the crossing had taken no time at all, or none that the atoclock, as configured, could detect. This was significant not because it ended the debate. It did not. But because it brought the cleanest available system to bear on the question and found, within its uncertainties, a result compatible with the near instantaneous picture. And yet the debate did not end. It continues still. Part of the reason is interpretive. Even with hydrogen, the question of what the atoclock's angular offset actually measures, whether it cleanly isolates the tunneling delay from all other effects, whether the theoretical subtraction of the Coulomb contribution is as model-independent as the hydrogen experiment hopes, remains a point of genuine technical disagreement among physicists who have spent years studying exactly this question. Some argue that even the hydrogen atoclock cannot fully separate the tunneling delay from the Coulomb field interaction during the exit process, because those two things are not cleanly separable. The electron exits the barrier into the field of the atom, and the dynamics of exit and post-exit are intertwined in ways that resist decomposition by any purely classical model of the Coulomb correction. Other experimental approaches, using different systems and different measurement strategies, including some experiments with atoms in optical barriers, where a laser field creates a spatial region of high potential through which another particle must tunnel, and where the setup allows different kinds of timing measurements than the atoclock provides. have been read by some researchers as evidence for a small but non-zero traversal time. The reported values differ across experiments and definitions, ranging across fractions of a femtosecond to roughly a femtosecond in duration, depending on what system is being probed and what theoretical framework is being used to extract a time from the measured data. These are extraordinarily short intervals. A femtosecond is itself a thousandth of a picosecond, a millionth of a nanosecond, a duration in which light travels less than a thousandth of a millimeter. And yet, within that already vanishingly brief timescale, the question of whether the crossing takes some finite fraction of that time or none at all remains, as of now, unresolved. The richness of the disagreement is deepened by the fact that tunneling time is not a single concept with a single formula. It is a family of concepts, and different members of the family answer genuinely different questions. The phase time, sometimes called the Wigner delay or the Wigner-Eisenbud time, measures the shift in the arrival time of the peak of a wave packet that has tunneled compared to one that travelled the same distance in free space. The dwell time measures the average time a quantum particle spends in the barrier region, defined through the probability current, the flow of quantum probability. The Lama time uses the precession of a particle's spin in a weak magnetic field applied only inside the barrier as an internal clock. The amount of spin rotation encodes the time the particle spent inside the magnetic region, and therefore inside the barrier. The Bittaker-Landauer time is related to how the tunneling probability changes when the barrier's height is varied slowly, treating the adiabatic response as a temporal signal. These are not competing theories about a single thing. They are measurements of related but distinct physical quantities, each of which is well defined within its own framework, and each of which asks a slightly different question about what is happening inside the barrier. When one approach reports a time of essentially zero and another reports a small but finite value, the disagreement is not necessarily evidence that one of them is simply wrong. It may be evidence that they are measuring different aspects of the same phenomenon, that the quantum mechanical equivalent of how long did it take is not a single question with a single answer, but several distinct questions that happen to share an intuitive label. The Hartmann effect, first noticed theoretically in the 1960s, sharpens this strangeness in a particularly striking way. When you compute certain tunneling time definitions for a particle crossing a potential barrier and then make the barrier thicker and thicker, you find something that seems impossible beyond a certain barrier thickness. The computed traversal time stops increasing. Make the barrier twice as thick, and the phase time, the apparent delay in the peak of the transmitted wave packet, does not double. It barely changes. For very thick barriers, the phase time saturates, approaching a finite limit even as the barrier becomes arbitrarily wide. If you interpret this naively as an actual traversal velocity, distance divided by time, you get velocities that exceed the speed of light for thick enough barriers. For years, this seemed like a scandal. The Hartmann effect appeared to suggest that particles tunneling through thick barriers were somehow moving faster than light, a violation of special relativity so fundamental that it could not possibly be right. And indeed, it is not right, but for a subtle reason that takes some care to state. The phase time, it turns out, does not describe the propagation of information or energy. It describes the shift in the peak of a transmitted wave packet, and that peak shift can be misleading when the barrier is thick. What happens in tunneling through a thick barrier is a kind of pulse reshaping. The barrier preferentially transmits the earliest arriving components of the wave packet, the components that make up the leading edge, and suppresses the later arriving components. The peak of the transmitted pulse is therefore earlier than the peak of the incident pulse, not because a localized entity traveled at superluminal speed, but because different frequency components of the packet were filtered differently by the barrier. The leading edge gets through. The trailing parts do not. The peak appears early because the pulse has been reshaped, not because anything moved faster than light. No signal, no energy, no information crosses the barrier ahead of light. Causality is intact. The apparent faster-than-light result is a consequence of measuring the peak of a reshaped distribution, not a measurement of how fast a localized thing traveled. This reconciliation is accepted by the mainstream of the field. It is not controversial in the way that the tunneling delay itself is controversial. But it required careful work to establish, and the fact that naive interpretations of tunneling times can seem to suggest superluminal travel is part of why the popular treatment of this subject so often goes wrong. The claim that tunneling is faster than light is not a triumph of quantum strangeness over Einstein. It is a misreading of a subtlety about wave packets and peak positions. What is actually faster than light is a mathematical artifact of reshaping, not a particle racing through a wall. The distinction matters. The title of this film suggests that the crossing happens in almost no time at all, and that is the honest framing, the one the evidence actually supports. Not no time in a way that violates relativity. Not no time in a way that has been definitively measured. Almost no time, a duration so small that the best experiments humanity has built, the most refined clocks ever devised, operating at the frontier of what is technically achievable at the beginning of the 21st century, are only now reaching the resolution needed to say anything at all about it. And what they are finding is that the answer is still not clear. The physicists who received the 2023 Nobel Prize in Physics were recognized precisely for creating the experimental foundation without which questions like this one could not even be approached. Pierre Agostini, Ferenc Krauss, and Anne Lhuillier were awarded the prize for their work on generating attosecond pulses of light, for developing the methods and the understanding that allowed bursts of electromagnetic radiation lasting only a few hundred attoseconds, or in some cases only a few tens of attoseconds, to be produced and used as tools for probing matter. Lhuillier had discovered in the 1980s that when an intense laser beam passes through a noble gas, the atoms emit light at many harmonics of the laser's fundamental frequency, high harmonics, extending far into the ultraviolet, and that these harmonics, under the right conditions, could be made to combine into an extremely brief pulse. Agostini and Krauss, working separately and with different technical approaches, demonstrated how to isolate and characterize those pulses, how to confirm that they truly lasted for attosecond durations, and how to use them as strobes, as flashes brief enough to freeze the motion of electrons inside atoms, the way a camera flash freezes the motion of a hummingbird's wings. The Nobel Committee, in citing their work, described attosecond science as giving humanity the tools to study processes that were previously invisible not because they were too small, but because they were too fast. The electrons inside a hydrogen atom complete a classical orbit, a concept that is itself only approximate but useful for scale, in about 150 attoseconds. Chemical bond formation involves electron rearrangement on timescales of a few hundred attoseconds to a few femtoseconds. Without attosecond pulses, all of this happened faster than any probe could see. With them, it became, for the first time in the history of science, directly observable. and the question of tunneling time sitting at the intersection of the quantum measurement problem. Fundamental questions about time and causality and the practical reality of processes like solar fusion and semiconductor physics became, if not answerable, at least attackable. That the question remains open after more than 15 years of at-o'clock experiments is not a failure of the technique or the people applying it. It reflects something genuine about the question itself. And the most honest thing this film can offer, in the darkness of this late hour, in the quiet space between the last fact and the first softening toward sleep, is not a resolution that the scientists themselves do not have, but a clear-eyed account of why the question is hard in a way that goes deeper than experimental precision. When a physicist asks how long did the particle spend inside the barrier, the question sounds like the kind of question you might ask about a car in a tunnel. The car enters at one end, exits at the other, and the time between those events, measured on a clock outside the tunnel, is the traversal time. Simple, unambiguous, the clock outside is not disturbed by the car's passage, and the car is a localized, well-defined object with a position that exists independently of whether you look at it. A quantum particle is none of these things. It does not have a position inside the barrier in the way the car has a position inside the tunnel. Its position is a wave function, a spread of probability, and inside the barrier that wave function is not oscillatory but evanescent, decaying, not propagating. The particle is not traveling through the barrier the way a car travels through a tunnel. It is doing something without a classical analogue, something that the word travelling does not quite capture, something that the English language and the human visual imagination were not built to hold without metaphor. If you try to measure where the particle is while it is inside the barrier, if you try to set up a detector or a clock inside the classically forbidden region that can tell you the particle is here, now, you do something unavoidable. You interact with it. And that interaction disturbs the very crossing you are trying to time. The wave function that was quietly decaying through the barrier, maintaining its coherence, its continuity from one side to the other, is perturbed by the act of measurement. The tunneling event you are trying to observe is not the same event after your observation as it would have been without it. You cannot watch the particle inside the wall without changing what it does in the wall. This is not a limitation of current technology. It is not a problem that better clocks or more sensitive detectors will eventually overcome. It reflects something structural about quantum mechanics, the measurement problem, in its most concrete and physical form. The information you can extract about the particle inside the barrier is limited not by your instruments, but by the nature of the system. Different ways of probing the crossing, different clock designs, different definitions of tunneling time, disturb the crossing differently, and so they measure different things. They are not 10 imperfect measurements of one true value. They may be 10 measurements of 10 related but distinct quantities, each one answering a slightly different question about a phenomenon that resists being compressed into the single number our intuitions demand. This is the honest landing the dossier points toward, and the most satisfying one, not because it closes the question, but because it locates the source of the difficulty in exactly the right place. The reason nearly a century of theoretical work produced competing definitions instead of consensus is not that the theorists were confused. It is that quantum mechanics, when pressed on what it means for something to take time inside a classically forbidden region, does not give a unique answer. The reason at-o'clock experiments, using the finest temporal tools in the history of physics, produce results that different groups read differently is not that the experiments are poorly done. It is that what the experiments measure is, in a deep sense, entangled with how they choose to measure it. The question, how long did it spend inside, assumes a kind of fact about the particle's location at intermediate times that quantum mechanics in the barrier region does not straightforwardly supply. And perhaps that is the right place to rest. Not on the frustration of an unanswered question, but on the recognition that the question, in its simplest form, may be asking the universe to be more like a car in a tunnel than it is capable of being. The universe is, in this place, doing something subtler. The particle crosses because the wave function leaks. The crossing happens, in some sense, too fast to time, and in another sense too fundamentally quantum to be assigned a single duration. The sun shines because of this subtlety. The scanning, tunneling microscope reads individual atoms because of it. Flash memory stores your photographs because of it. Alpha particles sing to Geiger counters because of it. Enzymes in the dark interior of a cell carry out the business of metabolism because of it. The effect is real in every practical consequence it has ever produced. Only the single number, the crossing time, the duration of the transit, the lonely tick of the clock inside the classically forbidden zone, refuses to settle. There is something, if you sit with it quietly in the dark, that is not frustrating about this, but restful. Science at its frontier looks like this. Not a clean answer on a blackboard, but a collection of brilliant people with the finest instruments ever built, disagreeing carefully, measuring precisely different facets of a thing that is not quite what any of them thought it would be when they started. Ursula Keller at IBM Zurich, adjusting the polarization of a laser pulse until it rotates exactly like a clock hand. The authors of the 2019 hydrogen experiment, choosing atomic hydrogen because it is the one system theory can solve exactly, hoping that exactness will dissolve the ambiguity, finding that the ambiguity runs deeper than the atomic model. Pierre Agostini, Ferenc Krauss, Anne L'Huillier, each approaching the attosecond frontier from a different direction, each contributing a piece of the technical foundation, without which none of the experiments that followed could have run. And behind them all, reaching back through the decades, the theorists who asked what phase time and dwell time and Lama time and Bittaker-Landauer time each mean, who traced the Hartmann effect to pulse reshaping rather than to a particle outrunning light, who argued in the pages of physics journals over whether the question of traversal time was even well posed, all of them circling the same narrow gap, the same classically forbidden region, the same faint, exponentially decaying amplitude that refuses to be quite zero on the far side of the wall. When George Gamow sat down in 1928 and worked out that the alpha particle escapes the nucleus by tunneling rather than climbing, when he showed that tiny differences in energy produce half-lives ranging from microseconds to billions of years, that the same exponential sensitivity that lets the sun burn slowly also lets some nuclei decay in a flash and others persist through the age of the universe, he was not thinking about attoclocks. He was not thinking about IBM Zurich or circularly polarized lasers or angular streaking. He was thinking about a particle inside a nucleus, trapped by a potential it lacked the classical energy to surmount, and wondering how it got out. The answer was that the wave function leaked through. The particle tunneled. The question of how long that took was not yet, in 1928, even being asked. Nearly a century has passed. The question is being asked now, with tools so precise they must be measured in units that did not exist as practical quantities when Gamow wrote his paper. The answer is still arriving. Some of it came in a measurement of the angle at which a helium electron flew away from a rotating laser field. Some of it came in the exact wave function of a hydrogen atom, the simplest atom in existence, subjected to the most refined temporal probe physics has yet produced. Some of it came in a theoretical argument about whether peaks of wave packets and positions of particles are the same kind of information, and the careful demonstration that they are not. And some of it, perhaps the most important part, came in the recognition that the question sits at the boundary of what quantum mechanics, as currently understood, can cleanly answer. That boundary is not a failure. It is the place where the next physics lives, waiting, the way the alpha particle once waited inside the nucleus, for a thin enough wall to appear. Outside this moment, the world is quiet. Whatever hour has gathered around you, whatever softness of pillow or blanket or familiar darkness has settled in, the universe is doing what it has always done. Protons in the core of the Sun are pressing toward one another, most of them deflected by the Coulomb barrier, 1 in a billion or so slipping through on a timescale so slow that a given proton waits, on average, something like 1 billion years for its moment. In the tip of a scanning tunneling microscope somewhere in a laboratory, electrons are leaking across a vacuum gap, a nanometer wide. Feeling the heights of individual atoms through the tenfold change in current that a single atomic diameter produces. In the nuclei of radioactive atoms, alpha particles are pressing against barriers, most finding them too thick to cross, some finding a thin place and leaking through, each one that makes it registering as a click on a detector, tunneling made audible. In the enzymes folded inside every living cell, protons and electrons are tunneling between molecular sites, carrying out the quiet chemistry of metabolism in the dark. And somewhere, in a laboratory equipped with circularly polarized laser pulses and momentum-resolved electron detectors, some version of the Atterclock experiment is probably still running, still measuring angles, still trying to read, from the final trajectory of an electron, something about what happened during the few attoseconds, or fewer, when it was inside a barrier it had no classical right to enter. Still arguing, carefully and precisely and in good faith, about what the angles mean. The question that began with Gamow in 1928 and was sharpened by the Atterclock in the early 21st century is still open. Not because science is failing, because the universe, at this particular address, a potential barrier, a decaying wave function, a crossing that takes almost no time at all, or perhaps no time, or perhaps a small but real time that depends on what you mean by time, in a place where time, as classically understood, may not be the right concept, is telling us something true and strange, something that resists summary, something that rewards quiet attention more than it rewards a quick answer. You have spent this darkness alongside it. The sun will rise because protons tunneled. The chips that run the devices of your life were shaped by engineers who had to account for electrons tunneling where they were not wanted. The image of 35 xenon atoms spelling 3 letters on a surface was possible because a needle sharp enough to feel 1 atom through a leaking current was possible. All of it leaking. All of it crossing where it should not be able to cross, all of it doing so in an amount of time that the cleverest instruments and the sharpest minds of the attosecond era are still working to name. Let that be enough, for now. Let the wave function decay gently through whatever remains of the night. Let the answer be, for a little while longer, still arriving, because questions that have been open for 100 years deserve the patience of a night's sleep before they close. And if they never quite close, if the question of how long a particle spends inside a wall it cannot enter turns out to be one of those questions that the universe answers with a category correction rather than a number, well, that is perhaps the most interesting thing a question can do. The experiments will continue. The atom clock will keep turning. Somewhere in the spectrum between almost no time at all and a genuinely unmeasurable absence of time, the answer is being approached by careful people who have given their working lives to the problem, armed with laser pulses measured in attoseconds, with the Nobel-recognized technology for producing them, with the cleanest atoms and the most precise detectors available. They have not agreed yet. They will keep looking. And for now, in this quiet, that is enough to carry you gently the rest of the way toward morning. Sleep well, fellow voyager. The next journey keeps until you wake.